Hi, I'm Brandy Heflin. I'm a personalized physics instructor, and I help high school and college students feel confident and successful in learning physics. I'm here today with a student request of a kinematics problem about a patrol car catching a speeder, and we want to find out when and where they catch up with each other and how fast the patrol car is moving. There are actually two different ways to think about the setup for this problem, and I will walk you through both. So here is our problem setup. A speeding motorist traveling at 35 meters per second passes a stationary patrol car, and it takes the officer 3.0 seconds to begin pursuit with a constant acceleration of 3 meters per second squared. We want to know how long will it take the patrol car to catch up, how far will they have driven, and how fast will the patrol car be moving then. And so here's an animation. Our speeder passes the patrol car takes a few seconds and then begins to go, and eventually will catch up with our speeder. So we need to mark a few important positions and times. We need to mark when the speeder passes the patrol car, where the speeder is when the patrol car begins moving, and then that final position. And the important question we're going to answer here is, how do we express the relationships between where each car is and how much time has passed? So we can call this initial position where the speeder passes the patrol car x equals 0 meters, and we can also consider that a time of 0 seconds. That position where the speeder is when the patrol car starts will come into play later, but we do need to note that this happens, there we go, missed my pen. So this happens at 3 seconds. And again, this is the speeder's position when the patrol car starts. So let's express these position-time relationships with our mathematical models. So our speeder, of course, is constant velocity. So that's just going to be average velocity times time plus the speeder's initial position. I'm going to mark it X, not S, because it's the speeder. And our speeder, of course, had a velocity of 35 meters per second, and they started at 0 meters. So we can just finalize this to be the position of the speeder will be equal to 35 times t. Our patrol car, on the other hand, is going to need the equation for the uniform acceleration position-time relationship, which is going to be the initial position of the patrol car. I should have actually marked that v for the speeder, but it's going to be the patrol car's initial velocity times time plus 1/2 times the patrol car's acceleration times time squared. And just for completeness, I will come back over here and mark that Vs for the speeder. So here's the thing. Our patrol car started 3 seconds after our speeder did. So our patrol car's motion is happening for a different amount of time. And in order to solve this problem algebraically or graphically, we need to make sure that both equations are talking about the time in the same object's frame of reference. And so that might not be the best way to describe it, but the key thing here is that our time for the patrol car is going to be the time for the speeder minus 3 seconds. And well, we just use t to mean the speeder's time, so we're going to have to take away 3 seconds in our expression here. And our patrol car had an initial position of 0 meters, and an initial velocity of 0 meters per second. And then we'll have 1/2 times 3 times that t minus 3 quantity squared. And I'm just going to leave this for the moment as 1.5 times the quantity t minus 3 squared, and we'll expand that on a couple slides ahead when we get to the algebraic solution. So plotting those relationships is my favorite way to solve, and I will show you both. So let me share with you that I got online and went to a site called GeoGebra, which has a graphing calculator, like simulation capabilities, so that I could get these nice screenshots and then also use the intersection feature. So very clearly, this point up here is going to be the one that we're going to care about. And notice that we very clearly marked that this is when the patrol car started moving. So when we get this solution, whether we are doing it graphically or algebraically, we also need to notice that there's another intersection point right here. And this one has no physical meaning because we know our patrol car didn't start moving until 3 seconds. So our patrol car isn't going to have a position anywhere but 0 up until 3 seconds. And that means that when we get to the end, we will have an extraneous solution that we can disregard. And so, yeah, that patrol car's position we know was 0 meters up until 3 seconds. So we're going to ignore that point coming up. So here we go with our algebraic solution. In order to, oops, there we go. I lost my cursor. Okay. So we're going to need to set the position relationship for the speeder equal to that of our patrol car. And recall that we had a very simple 35t for our speeder, and I'd left our patrol car's relationship as 1.5 times t minus 3 squared. So we're going to have to go ahead and expand that now. And we will get 1.5t squared minus 9t plus 13.5. And unfortunately, yeah, we're going to get a quadratic equation. So we'll have two different ways that we can solve this after we rearrange so that the left side is 0. We'll have 1.5t squared minus 44t plus 13.5. And now our two possible ways to solve are to plot with a graphing calculator and get the roots. That, as you can imagine, is my favorite. Let the graphing calculator do the hard work. Or we can use the quadratic formula. And recall that the quadratic formula involves adding in the numerator and subtracting. When we add our quantities in the numerator, we get a time of 29 seconds. And when we subtract, we get 0.31 seconds. So that is that extraneous solution that has no physical meaning because we know our patrol car hadn't started moving yet. So we're going to disregard it. All right, so that's our time. Let's find our positions where they meet. We need to substitute that time into one of our position time relationships, I'm going to choose it for the speeder because there will be less mathematics to do. If I can avoid squaring things, I like to. And that's going to get me 1,015 meters. And then last but not least is going to be the final velocity for our patrol car. So we need to recall the velocity time relationship for uniform acceleration, which is of course going to be acceleration times elapsed time plus the initial velocity. So we'll take that 3 meters per second squared, but pause. Remember that our time the patrolman moved is going to be the time the speeder moved minus 3 seconds. So our patrol car only moved for 26 seconds. Our patrol car, let's try spelling patrol correctly there. Sorry, not part troll. So our patrol car didn't move for the full 29 seconds. They only moved for 26 seconds. So we'll want to make sure to plug in the correct time there, and we get a final velocity of 78 meters per second. And let me mark for clarity by circling what were the 3 answers that we were asked to find and that we successfully solved. Let's go check out what GeoGebra had to say. So here's that graph again, and oops, come on, there we go. So GeoGebra gave us pretty close to exactly the same answer. I rounded a little bit differently. So notice GeoGebra said 29.02 seconds. I rounded down to 29, which meant when I found my position, I did get something a little bit less than GeoGebra did, but folks, that's a less than 1 meter difference over more than 1,000 meters. That's 0.1% off. 1 meter out of that many meters is really an acceptable answer. So it would be fine to report this as 29 seconds and 1,015 meters. And then again, notice that I want to highlight for you that we do have, let's get back to the pen tool instead of highlighter, that we do have, right, this is the B that we're going to ignore. And then up here is that solution A that matters. And again, that reminder, we're going to ignore B because this point right here shows when our patrol car actually started moving. So as promised, there is a second way to think about these position-time relationships. So recall that I marked that blue line before and called that, well, that's the 3-second mark. That's when our patrol car starts moving. But what if we let this be the position we consider 0 meters, because we're going to define things in terms of what the patrol car is doing instead of what the speeder's doing. And so we'll call this our time of 0 seconds, but it's still important that this green line is when the speeder passed the patrol car. So this matters. This is actually going to correspond to a time of minus 3 seconds, right? Because our speeder passed our patrol car 3 seconds before the speeder actually took off. And again, let's have that reminder that this is when the patrol car started. And so our speeder is going to have a displacement during that 3 seconds. And I'm going to call that delta XS. And we're going to need to find that in order to amend our position time relationships. So our speeder is going to have traveled for 3 seconds at 35 meters per second and gone 105 meters before the patrol car starts. So that's the speeder's position when the patrol car begins. So when we think back to our position-time relationship, and remember that it's going to be velocity times elapsed time plus initial position, well, this initial position is going to be in from the perspective of what the patrol car is doing. So that's going to be that 105 meters, right? So what we're considering time 0 for our patrol car is, 3 seconds after our speeder actually passed the patrolman. So our position time relationship is now going to be 35t plus 105 meters. And just like we had, we had that correction for the time before because we were putting everything in terms of what's going on for the speeder. Now that's our correction for our speeder when we're putting everything in terms of what's going on for the patrol car. And so our patrol car's relationship now becomes much easier. We had, v naught t plus a half a t squared. Oh yeah, and we've got to include that initial position. Well, our patrol car had initial velocity of 0. They have their acceleration of 3 meters per second squared. And now we don't have to correct the time. And they, of course, did start at 0 meters. So now our patrol car has a relationship of just plain and simple 1.5 t squared. So let's check in with GeoGebra. And again, let's highlight the fact that we have now the vertex of our parabola, of our, the plot of our quadratic relationship is at 0 because we're now putting things in terms of what's going on for the speeder. And the speeder begins moving at time 0 and is at a position of 0. And then notice over here, here is our t equals minus 3 seconds where our speeder actually passed our patrolman. And then over here is going to be that final time and position that we're going to go find. So away we go. We have our speeder's relationship. This time was that 35t plus 105. And we're going to set that equal to our patrolman's relationship, which our patrolman this time was just 1.5 t squared. Oops, finish the squared. So yeah, we can't get away from the quadratic relationship. So we'll get 1.5 t squared minus 35t plus 105. Again, you've got the option, 2 ways to solve. You can plot and get the roots, or you can, I'm going to abbreviate quadratic formula, and when you add in your numerator for quadratic formula, you are going to get 26 seconds, which makes sense. It's 3 seconds less than before because before we were defining time in terms of what the speeder did. Now we're defining time in terms of what the patrol car is doing. The patrol car moves for 3 seconds less than the speeder. Hooray! So we will get, when we subtract in our numerator, negative 2.69 seconds. So once again, this one is that extraneous solution that has no physical meaning, so we will disregard it. We have a time. Now we need, where are they? Where did they meet? Once again, I need to pick a position-time relationship. Okay, I could do 35 times 26 plus 105 for the speeder, Or, you know, it's not going to be so terrible to do 1.5 times 26 squared. That's actually going to be fewer keystrokes on the calculator. So I am going to get, once again, 1,015 meters. And you can, you know, if you felt the need to, you could double check that with the speeder. And then our last step is going to be, once again, to get our patrol car's final velocity using the velocity time relationship for uniform acceleration. And we're going to do 3 times 26 plus 0 and get 78 meters per second. And GeoGebra says 26 seconds, 1,015.81 meters. Again, same thing that we had before. I rounded, GeoGebra didn't. That's why we got that little bit of extra. And notice that once again, yep, there is, oops, I need the pen tool back, not the highlighter. There is this, you know, extraneous solution that we will disregard because it's before our patrol car ever started. And then this one up here is the one that we want. So let's do a little reality check here. Our speeder's velocity is only about 78 miles per hour. And the patrol car's acceleration is at the low end of the acceleration for the average acceleration of a passenger vehicle, which is 3 to 4 meters per second squared. Our patrol car's final velocity is 174 miles per hour, which is faster than the top speed of any police vehicle on the road in the USA today. So clearly this was a physics exercise and a few things were a little disconnected from reality. And like, seriously? Would a car going 78 miles per hour, even if they were in a school zone, warrant the slowest acceleration and a beyond vehicle capabilities top speed? Oh, and a patrol car waiting 3 seconds to take off? So you can look up the times that it takes the top 2 police vehicles in the U.S. To go from 0 to 60 miles per hour. The Ford Police Interceptor has a top acceleration of 4.65 meters per second squared and a top speed of 150 miles per hour. And the Dodge Charger has a top acceleration of a little bit less, 4.57 meters per second squared, and a top speed of 149 miles per hour. So if this were a police car that were an interceptor and it were accelerating at 4.6 meters per second squared, our patrol car could wait 1 second and catch the speeder in just under 14 seconds, and they would reach a top speed of 64.29 meters per second, which is 143.75 miles per hour. But more realistically, our patrol car is just going to reach a top speed that's greater than that of the speeder or equal to, and then they're just going to continue at that speed rather than catch up while they're still accelerating. You know, and an observant patrol car, patrolman is going to see the speeder coming and probably be able to start moving as soon as the speeder passes or even already be in motion. You know, so that's just something to consider for, you know, the reality check of, do our answers make sense? So I hope you found today's explanation of the solution for this very typical introductory kinematics problem helpful. If you have a video solution request, whether it's a piece of content that you'd like to have explained or a problem you'd like to see solved, you can email me at physicsproblemrequests@gmail.com. If you'd like some email assistance with a problem you're working on, you can reach me at freephysicshelpline@gmail.com, and there's a limit of 10 questions per academic year. To learn more about my online physics tutoring services, you can email me at brandyheflinphysics@gmail.com. You can visit my website, virtualphysicsofficehours.com, or you can find me on Facebook. I'm Physics Tutor Brandy. I love physics, and I love helping you. Until next time.